Welcome back to Grade 7 Math, 2014-2015. In this presentation, we will introduce Module 1, entitled Ratios and Proportional Relationships, and talk about some big ideas. Okay, so get ready, grab your math journal and a pencil so you can take some notes and do a few problems as we move along. Okay, so big idea number one I would like to investigate is this, and read along with me, and maybe stop and discuss it with your teacher if there is any misunderstanding. So big idea number one is this: a ratio is a comparison of any two quantities, and we're going to hear this word compare a lot. A key developmental milestone, and that means for you guys, boys and girls, milestones are, understandings, kind of epiphanies in a sense when you come to understand this. But one of those key developmental milestones is the ability of a student to begin to think of a ratio as a distinct entity. And that means a distinct entity means its own thing, okay? Its own thing, this idea of distinct entity, right there, distinct entity, its own thing. So it is different than the two measures that make it up, because you may know already, you may have a ratio that is 2 to 1. Now you have, I don't know what these are because they're just arbitrary, but you have this quantity and this quantity, and then you have the ratio itself. So it is a distinct entity and can be used in many, many ways. Okay, so we'll just move on from there. And again, if you need to, talk to your mom or dad about that, please go ahead. Okay, so for example, this idea of comparing. Okay, so how do these circles compare? Oops, put the wrong one in there. When will I stop doing that? How do these circles compare? If you want to go ahead and stop the video, you can stop it right now and just take a look and talk about it. Just remembering that a ratio is a comparison of any two quantities. Okay? Okay, so maybe some of the comparisons you came up with is you compared the blue circles with the black circles. And in that case, you could have said there were four blue circles for every 3 black circles. You could have said there were 3 black circles for every 4 blue circles. Again, you see I'm using ratios, and instead of saying 2 every time I see the colon, I am saying for every, okay, which is kind of what it's all about. Okay, so what are some other things you could have said? You may have counted all of them, and you counted 7. So there were 7 circles, and 4 of them happened to be blue. So you could have said there were 4 circles for every 4 blue circles for every 7 circles entirely. Okay, looking at ratios in different ways. Okay, but again, comparing all the time: blue to black, black to blue, blue to the whole. Okay. All right. So again, going forward, again, you may have noticed the way I presented those ratios in the prior slide. I did it in 2 ways. The last one I did when I compared the blue circles to the total number, I was thinking part to whole. Okay, I was thinking part to whole. So if I was to write a part to whole ratio for blue, like I did before, I would say 4 to 7. Okay. Now what I'm implying here is that let's say this is a set of circles that you can buy in a store, a little baggie of circles, for children to play with or to do math with, whatever. And this was the ratio that they used. They used a ratio of 4 blue to every 7 total. Okay, every 7 total. All right, so that would mean if I had, and again, the total bag here in this case is 7. All right, 7 is our total. But if I made our total 14, if the total was 14, let's say I had a bag of 14, using this ratio right here, our 4 to 7 ratio, okay, I would then know that there would be 8 blue in that bag of 14. Now, if this ratio applies, okay, you can't do that with a bag of M&Ms if you've ever tried those small bags. And they got all the different colors, and you never get a real standard ratio in there of blue to the total, or brown to the total, or red to the total. They're always varied, but at times, and you'll see in the future, ratios and staying true to a ratio is very, very important. Okay, so again, thinking of this right here, this 4 to 7 as a distinct entity, okay, its own thing. We can just carry it, and what we are creating when we say 8 to 14, we're creating something called equivalent. If I could get this to right here, equivalent ratios. Okay, because it's equal, it's the same. Okay, it's the same. 4 out of 7, 4 over 7 is the same as 8 over 14. Okay? Yikes. Okay, I'm not sure exactly what happened there, but yes. Here we go. And so again, thinking about how these circles compare here, we can talk now about part to part, like we talked about part to whole before. Again, and reiterating from before, a ratio is different from the two measures that make it up. Okay, so if we were going to do part to part here, one part of this group are the 4 blue circles. Another part are the 3 black circles. Now, when you add these up, there are 7 total. 4 plus 3 equals 7. But the other way around, if you were going to do black to blue, it would look like that. Okay, so you have part to part. Okay, part to part. So for every 3 black, there are 4 blue. We can extend that out. If I knew for every 3 there were 3 black, there were 4 blue, how about if I had 6 black? Then I know I would have 8 blue. Again, if that ratio held, that 3 to 4 ratio held, I would know, and I'd be able to extrapolate or be able to look further and to tell. So, for example, if I knew there were 300 black, I know that there were 400. There would be 400 blue. Okay, so 3 to 4. Okay, 3 to 4 is our ratio black to blue. 4 to 3 is our ratio blue to black. Another real interesting thing, if you went ahead and made fractions out of these, the blue to black ratio would be 4 over 3, or 4/3, and the black to blue ratio would be 3 over 4, or 3/4. And it would become very clear that there were more blue, because the blue represent 4/3 of the blacks, which is more than 1. Okay, but the blacks represent only 3/4 of the blue. Okay? Alrighty, so big idea number 2 is this. Proportional thinking is developed through activities involving comparing and determining the equivalence of ratios and solving proportions in a wide variety of problem-based contexts. Okay, this idea of problem-based contexts, all right? It's the way you develop it, and we can just continue to write down, 3 to 4 is equal to 6 to what? We continue to do that over and over again, but we may not really learn very much, okay? But if we go ahead and we compare and determine equivalence of ratios in a wide variety of problem-based contexts, that is more effective. Okay, so let's go ahead and do some of that. Okay. All right, here we go. So let's do one. A recipe for lemonade calls for the juice of 6 lemons and 4 cups of water. Okay. So here's my question to you, and I want you to just pause after I read the question and talk to your parent teacher about it, and just jot down some thoughts in your workbook, okay, in your notebook there. All right, here we go. So how could you use ratio to show the relationship between the amount of water and the number of lemons used in this recipe? Okay, so you want to create a ratio that could be used for any amount. Swimming pool full of lemonade. Apply a ratio, or what ratio could you apply to make sure you have the same recipe? So go ahead and take a few minutes. Okay, so what did you get? You may have created a ratio, and I'm hoping you did, using some key numbers here. We have the juice of 6 lemons, 4 cups of water. So you could have went ahead and said the ratio for this delicious lemonade is 6 to 4. Now, unlike past problems we've had, like the rings, the circles, they're all circles, blue circles, black circles. But I guess they're different things, but they're more similar than lemons and cups of water, okay? But this ratio right here, this 6 to 4 ratio, 6 lemons to 4 cups of water, could apply and could again be used to make any number of recipes, okay, or any number of different quantities of lemonade, okay. All right, so recipe for lemonade we have up there. Remember, it is helpful, as we had said before, to think of a ratio as a distinct entity. This idea of a distinct entity again, something other than the number it represents. So let's consider this scenario down here. If I have 18 lemons and I want to squeeze them all, how much water would I need to mix with them? Okay, I have 18 lemons, I want to use them all. I go ahead and apply my ratio, and right now I have a ratio of 6 to 4. The 6 being the lemons, and the 4 being the cups of water. Okay. Now I have 18 lemons here. So what I'm making, and you might have recognized this, I'm going to make an equivalent ratio. Okay. So if I have 6 lemons here, and I have 18 here, I could easily recognize that that is 3. 18 is 3 times 6. So I need to go ahead and do the same to the 4 cups of water. And if I multiply that by 3, I get 12. Okay. So now I know that if I have 18 lemons, I want to squeeze them all and use them, I would need 12 cups of water.